Hello everyone, today's topic is X-ray diffraction. If you want to be a crystallographer or crystal analyzer, you should be able to determine crystalline substances because 90% of the samples are in crystalline form. After completing this lesson, you will be able to understand how the X-ray diffraction technique is used to determine crystalline substances. Please watch this video till the end. If you have any doubts, please ask me in the comment section below and don't forget to subscribe to my channel. Let's jump into the main topic of X-ray diffraction. X-ray diffraction is a rapid analytical technique that is primarily used for determining crystal structures and lattice parameters. In order to determine crystalline structures, two important requirements must be met. They are a beam of X-rays and X-ray diffractometer. The first experimental requirement is a beam of X-rays. There are many electromagnetic radiations such as UV radiations, visible radiations, and infrared radiations, etc. But these radiations will not cause any diffraction in the crystal. Only X-rays can produce diffractions in the crystals because X-rays have wavelengths that are similar to the crystal's interplanar distances. The X-ray diffractometer is the second most experimental requirement. Many X-ray diffraction patterns of various crystalline substances can be seen here. Each substance has a distinct or unique diffraction patterns which can be used to identify crystalline substances. At the end of this lecture, I will demonstrate you how to use an X-ray diffractometer to identify an unknown crystalline compound. When it comes to the production of X-rays, we know that X-rays are critical requirements for the X-ray diffraction process. X-rays can be generated by fast-moving electrons colliding with metallic targets, and as a result, X-rays are produced. Röntgen is a German scientist who accidentally discovered X-rays while performing experiments on cathode rays and named these rays unknown rays as X-rays. The metallic target will produce two types of X-rays. They are white X-rays and the characteristic X-rays. But these white X-rays are ineffective since they cover the entire wavelength in the spectrum. They do not produce distinct wavelengths, whereas characteristic X-ray shows a specific wavelength that are useful for identifying the crystalline substances. As we can see in this image, K alpha and K beta are the characteristic X-rays with a specific wavelength, whereas white radiations covers the entire wavelength range from 0.2 to 1.4 angstrom units. The wavelength of these characteristic X-rays differ depending on the metallic target. As shown in this table, molybdenum metal has a wavelength of 0.71 angstroms, copper has a wavelength of 1.54 angstroms, and so on. The second experimental requirement is an X-ray diffractometer. In crystalline materials, there is three methods for detecting X-ray diffraction. Van Leeuwen method, the first one. Second one is rotating crystal method and powder method, in which the powder diffraction method is the most commonly used one. Coming to the first diffraction method, that is Van Leeuwen method. Only single crystals can be examined using this method. Polychromatic light is transmitted through a single crystal. The detector is positioned at the fixed angle. Coming to the second method, that is rotating crystal method, which employs a single crystal as well, but a monochromatic beam is passed through it and the detector is positioned at variable angles. Coming to the final method, that is powder method, it is a sophisticated and useful method. This method is simple to use for analyzing polycrystals. We can send a monochromatic beam through a crystal and place the detector at a variable angle. In this image, you can see various diffractions of polycrystalline substances using the powder method. How does diffraction happen in a crystal? I will show you how diffraction patterns are formed by crystals. Lawrence Bragg is a physicist who invented Bragg's law in 1913. What is Bragg's law? how this Bragg's law explains diffractions in crystals. When a monochromatic X-ray beam strikes an atom in the crystalline lattice, each atom becomes a source of scattering radiation of the same wavelength. When the path difference between two reflected waves, so here we can see the path difference between two waves which are equal to the wavelength of X-rays, so that gives diffraction happens. So here n lambda equals to 2d sine theta. So this is a Bragg's law. So in which n is an integer, lambda is wavelength of incident X-rays, and d is interplanar spacing. There are two types of interferences that we can see in this Bragg's law. The first one is constructive interference and the second one is destructive interference. When two X-rays are going in the same phase, so these two X-rays will be combined and forming a big peak that is called constructive interference. So when two different oppositely going two phases are added together and forming a destructive interference. So when there is a constructive interference, we can get the peak. When there is a destructive interference, we cannot get any peak in the final spectrum. We learned about the X-ray diffraction theory. We will now look at how this information is used to identify an unknown sample. The sample preparation is the first step. Place a few milligrams of unknown crystalline material in a mortar, grind it into a fine powder, and place the powder in the sample holder. Then uniformly disperse it with a glass slide, and finally place the sample holder in this location in the X-ray diffractometer. This is the location so where we can put sample. Now we need to send a monochromatic light through the sample and move the detector around these different angles and record the diffraction patterns of the sample. Finally, interpret the diffraction patterns using the sample to determine the compound. This is the whole process. But how do you put into the practice? How to interpret diffraction patterns of crystalline substances. I will show you how to interpret diffraction data in this section. Here we can see XRD peaks and the data that goes with them. Each crystalline material has its own set of d-spacings which must be noted. First, based on relative intensities, so we must identify three strongest peaks. Here we can see the three strongest peaks. We now use d-spacing values, so from this data, to search a database of thousands of powder diffraction patterns of crystalline substances to identify the name of the unknown sample. And here we got three strongest peaks, that is 2.82, 1.99, and 1.63 angstroms. So by using these three values, so finally, so we can get different types of different samples. So but exactly here, these three values will be matching up with this NaCl. So finally, so we can conclude that NaCl is the compound that we have identified by X-ray diffraction technique. So this is about X-ray diffraction technique. Thank you.